So today we are going to have our lecture number 9. So far we have talked about algebra on matrices, how to add, multiply, subtract. And we learned about some special operations like the transpose operation. So I'm just trying to recall things that we have seen so far. Now, once we have done multiplication on matrices and all that, remember the idea of matrices has been primarily for us to solve the system of equation. So first things first, let me first help get one thing fixed for our notation purposes. If you look at a system like this, using matrix multiplication, I can write the system as 1 to 1 minus 1 multiplied by the column vector xy equal to the column vector 3, 4. Okay. The reason for using this notation is it's very useful in kind of helping us use things which we are familiar with, and that can help us do more algebra on matrices. So for example, this matrix over here that I have written, we will call that as the coefficient matrix. We have been calling it as coefficient matrix, so nothing new. The vector xy, we will denote it by the vector x, and the right hand side vector generally we denote by b. So any system of equations can be written in the form ax equal to b, and this should remind us of the kind of equations we generally see, 3x equal to 2. So here is your a, here is your x, and here is your b, and we love to solve these equations because we know how to solve them. So let us ask ourselves a procedure. How do we solve some equation like this? Generally speaking, you will say, oh, I'm going to divide by a. Dividing by a for us means the same thing as multiplying by the inverse of a on both the sides. So if I have an inverse of a, then I will say that, oh, this is 1. 1 times x is b over a. And hence we will call the solution as b over a. Or let me write it as b times a inverse, just so that we are kind of in the habit of thinking about inverse functions. Okay. Now, having said this, apart from the analogy that I have drawn over here, is there something more that we want to achieve? See, we can write our matrix, our system of linear equations in the form ax equal to b. One may attempt so we might want to think about solving ax is equal to b as, what if there was something which I can multiply? Let me call that matrix as M. Can I multiply by my matrix M on the left hand side and also on the right hand side, such that this product turns out to be just acting like 1? Remember the identity matrix. So can we have something like this? If yes, then wouldn't you agree that we would be able to solve for x just pretty much like the way we solved for x in those kind of equations? So this is our hope or a strategy. Can we do something like this, in the sense, can we find such a m which can do all we want? So here is what we want to achieve. This is our aim. can we find a matrix M such that M times A is the identity matrix? Now, this question seems kind of innocent question, but it has a lot of ramifications. First of all, you have to keep in mind that we can't simply multiply two matrices whenever we want. Their sizes should be compatible. The other thing we want is, or we should be cautious about, is that the two matrices, when they multiply, they need not commute. So that means when I want M times A to be identity, is it necessary that I will have A times M also as identity, or is it something that may or may not be there? So we have to come up with a proper definition of what an inverse would be, and then we will see under what circumstances inverse can exist for a matrix. So bottom line is we are trying to talk about inverses of a matrix in the multiplicative sense. So let's keep this question in front of us, and we'll try to coin a definition of an inverse. So here is what we want to achieve. We want the inverse of a matrix. So we want to ensure that whatever matrix gives us identity should give identity from both the sides. Now this may seem a bit unnatural at this stage, but why am I forcing? Because most of the time I will be multiplying it on the left. But there is a little more structure into these things which can be better understood when you take higher courses, why we need the idea of both left and right inverse as part of the definition. So I want a matrix M which can do this thing for me, and this kind of forces something. This forces that A must be a square matrix of size n by n, and M also should be a square matrix of the same size, because we want both the multiplications to be defined and make sure that the product turns out to be identity. Okay. So first question is, does everything have an inverse? So here's the question that we want to ask. Will every square matrix have an inverse? Second question we would want to ask is, see, asking important questions is very good for mathematics or understanding of it. So if the inverse exists, how to find it? Do we have a procedure by which we can find the inverse? Other question we want to ask is, okay, fine, I have an inverse. We want to ask the following question. Can something be said about the solutions? These kind of systems. One of them is the non-homogeneous, and the other one is the homogeneous system. So can something be said about the solutions of these guys when the matrix is invertible? Okay. So let's see, out of these questions, which one of these we can answer, which one of these we will have to postpone for some time, or maybe which one of these are difficult to answer at this stage. Let's see. So first thing first, will every square matrix have an inverse? Let's try it on a simple example. So let's try on a simple example. Let's take a 2 by 2 matrix. Say something like 1, 0, 0, 3. Does this matrix have an inverse? In the sense, can I multiply this matrix by another 2 by 2 matrix on the right and also on the left and get the identity matrix out of it? Can we do something like this? Now, of course, we can try to do it the long way. So let's try to do it once. Suppose this is my matrix that I'm going to multiply in order to achieve what I want. If I perform this matrix multiplication, what I'll get is basically A, B, and let's see, 3 times C and 3 times D. Okay. If I perform that multiplication, let's see what I'm going to get. A and 3B and C and 3. Notice that both multiplications have kind of given us different looking matrix, but we want both of them to equal the identity matrix. So if I compare these with the identity matrix, one thing is clear, that A must be 1, B must be 0, because once B is 0, both these entries will be 0, so they match. C should be 0, same idea. If C is 0, then both these entries match 0. And D must be 1/3. So in that case, both these matrices turn out to be the same identity matrix. So we can say that the inverse of the matrix 1, 0, 0, 3 is the matrix 1, 0, 0, 1/3. So at least we have some evidence that there are matrices whose inverse exists. So we are not searching things in total vacuum. There is something to it. Of course, this also tells us a possible way to find the inverse if it exists. What we did was we just went on computing all the entries of the matrix. But as you can see, even for a 2 by 2 matrix, I had 4 variables to worry about. Imagine if I want to find an inverse of a 10 by 10 matrix. If we use something like this, it will require a lot of equations, a lot of unknowns. In fact, it will be 100 unknowns. And solving it one at a time will be a nightmare. So there must be some better way of handling these kind of things. But could there be a matrix which does not have an inverse? Of course, you will say, oh, how about non-square matrices? So let us be more careful. Could there be a square matrix which does not have an inverse? Because we are only talking about inverse of a square matrix. So let's try our luck and see if we can find a matrix for which there will be no inverse. There is one answer which is obvious, but that is not what we are looking for. So the obvious answer could be that, well, if you look at the 0 matrix multiplied by anything will give you 0, so it will never give you identity matrix. So I can say for sure 0 does not have an inverse. But the reason we are not interested in that is because as it is, even in real numbers, 0 does not have an inverse, so we don't divide by 0. So out here we can also say, well, let us forget about zero matrix. What about non-zero matrices? Does every non-zero matrix have an inverse? So let's try our luck with similar looking example that we had. Can I have a matrix multiplied to this guy which can produce me the zero, which can produce the identity matrix? Now, any bit of matrix multiplication will be able to convince you that the product of this matrix will have a zero row. You can think of it in many ways. We talked about the rank of a matrix. The rank of this matrix is only 1. So it has a zero row. So upon multiplication, the rank cannot be more than what you started with. That's one way of looking at it. Or you can say, just by simple multiplication, this is what I get. So these guys can never be equal to each other. Hence, there is no matrix which can be multiplied to this guy to obtain identity. So our conclusion is this matrix is not invertible. You may say, well, I'm not really being honest here. I have lots of zeros in my matrix, and that is why, what if I really have a matrix which has every entry as non-zero? Could then it have a inverse? Let's try that. How about 1, 2, 1, 2? Can this matrix have an inverse? Well, if it did, then would you agree, if I multiplied by any matrix M over here, if you remember your matrix multiplication, the multiple ways by which we did the job, we said the matrix out here would be basically a linear combination of the columns of this matrix. Since both the columns are multiples of 1, so would you agree whatever I get over here would be basically a multiple of the vector 1, 1. Likewise, whatever I get over here would be a multiple of the vector 1, 1. And as you can check, that this cannot be equal to the identity matrix. So even though you have non-zero entries everywhere, still this did not turn out to be the identity matrix. Now I have given you a slightly different argument is because I want you to keep remembering various ways in which multiplication can be performed, and it will help you enhance your thinking in these kind of matters. Okay, so this is kind of a problem for us. Not every square matrix will have an inverse. That means we have to come up with a criteria which square matrices will have inverse. The second thing is, once we know there is an inverse, we have to find a way to compute it. Okay. So I'll try to develop some criteria for inverses and see if they are going to suggest something for us. Okay. So for our discussion from now on, anytime I say a matrix A, it will be a square matrix of some size. So I won't be repeating the word square matrix over and over again. And in case I need to highlight that we are talking about a general matrix, I will tell you the size of it. Okay? So let's make sure that we focus on square matrices only. Now, let's see the first criteria of a invertible matrix. If A has an inverse, that means I can multiply this guy to get 1, 0, 0, 0, 0, 1, 0, 0, so on and so forth. Okay. This is what our thing is. Now the matrix that I'm going to multiply will have some vectors over here. So let me call them as V1, V2, Vn. Now, if you recall your matrix multiplication, the matrix, when it is multiplied to another matrix, it can be thought of as A is acting on the vector V1, then A is acting on the vector V2. Remember, it's the linear combination of the columns of A, and A is acting on the vector Vn. This is how we can think of this matrix multiplication, and we want it to be equal to 1, 0, 0, 1, 0, 0. Okay, it will be clear in a moment where we are heading. If you match this matrix with that matrix, what are you looking for? You are saying A times V1 gives me the first vector 1, 0, 0. Then A times V2 will give me the second vector 0, 1, 0, 0. And if I continue like this, A times Vn will give me the vector 0, 0, 0. These vectors, they are all unit vectors. There's a special name for them. They're called the standard basis vectors. Right now we may not understand the significance of this name, but let us think of them as the nice vectors which tell you a lot of things about the space. Okay, look at this, what we have achieved. If my matrix is invertible, then that means this is what will happen. Let us look at each thing in a slightly different perspective. Would you agree that right now I am saying that if I look at the system given to me over here, then for this system, Ax equal to 1, 0, 0, V1 is a solution. Okay? That means I'm saying that this system must be consistent. Likewise, would you agree, out here I'm saying that the system of equations given by Ax is equal to 0, 1, 0, 0 must be consistent. And if it is consistent, it has a solution V2. So this tells us that if I am looking for inverses of a matrix, or inverse of a matrix, then it should satisfy some criteria. Okay, so here's my first observation, or you can say my first proposition. I claim that A is invertible if and only if Ax equal to Ei is consistent for all I from 1 to n. Now before we end up get lost in the details, let me first tell you what is the vector Ei. This is a notation I'm using to represent this unit vector. So all the entries out here are 0 except the ith entry. The ith entry is 1. Okay. Think of your x and y axis. You represent the x-axis as 1, 0, y-axis as 0, 1. So this is just basically the representation in n dimensions. So here is your x and y-axis. This direction we call as the 1, 0 direction. This direction we generally call as the 0, 1 direction. And if you are in 3 dimensions, you will have 1, 0, 0, 0, 1, 0, 0, 0, 1. So these are standard vectors in the respective dimensions. So we are saying that if you can guarantee that these systems will be consistent, then the matrix will be invertible. And in fact, if you look at the construction we have done, the solutions of this these systems will actually be the inverse of the matrix. So in some sense what we have done is, we have linked the existence of the inverse, or finding the inverse, to solving system of equations. Okay. So at least this gives us a possible way to solve or to check whether things are going to be invertible or not. So let's try to attempt this idea and see what does this give us. Okay. Now, what I'm going to suggest is a kind of a reminder of things we have seen before, and if we can possibly use our knowledge of row reduction, life will be very, very simple or very, very easy. So let's try with a simple matrix, say 1, 2, 3, 0, 5, 7, and 1, 0. Suppose somebody gave us this matrix. Is this matrix invertible or not? So I'm trying to figure out whether these systems, whether I can solve these systems, or whether I can guarantee that these systems are going to be consistent or not. So these are the three systems. If these are consistent, then I'm all set, and I will be able to say that this matrix will be invertible. In fact, I will be able to find the inverse also. If any one of them fails to be inconsistent, then according to the proposition we are claiming, the matrix cannot be invertible. So how do you solve a system like this? You will generally say, oh well, I'm going to make an augmented matrix, and I'm going to solve this using row reduction. So what will you do for this one? You'll say, oh, I'm going to create another augmented matrix. So only thing that gets changed is basically the right hand side. This is what happens, right? You'll be questioning, why am I not completing the other bracket of the matrix? If you see, let me remind you of the fact that we have seen before. The row reduction, you want to reduce it to a row echelon form. The row reduction that you perform is only dependent on the coefficient matrix. It doesn't depend on the right hand side. So that means whatever row reduction I would have done over here to solve the system, I would be using the same row operations over here to solve the system. So if you are going to do the same thing over and over again, why not just do it all together? Why not just perform so-called an extended augmented matrix, if you will, and just perform this operation for all three of them together and see what happens. If we can do this, then that means we will be able to get what we want. Okay, so let me erase this matrix now that we are going to do all these things together. So let's see if we can solve this using our operations of row reduction. I will use all the elementary row operations that we have seen. Okay, so we already have a pivot in the first row, so nothing there. Then I will use minus row 1 added to row 3. and this will give me 0, minus 2, minus 1, minus 1, 0, and 1. Okay. So at least I have achieved that in the first column I have one pivot. Now, if I go a little further, I try to see what can I do with this guy. 5, okay. Let's see. 1, 2, 3, 1, 0, 0. Suppose I divide by 5 throughout. Remember, that's a valid row operation, so there is nothing stopping us from doing it. And similarly, I divide by minus 2 over here. So I will have 1 half, 0, and minus 1 half. Okay. Even before we proceed, remember our only aim is to figure out whether these three systems will be consistent or not. Let us recall one fact. If you look at a system, let us hide these two for a while. If you look at this system, what thing will ensure that I will have a consistent system? Well, if I have pivots in every row over here, or in other sense, if no pivot goes on the right hand side of this bar, then would you agree that the system will be consistent? So I need a pivot in every row. Or in other words, I want the rank of this matrix to become 3. If I have rank 3, I'm guaranteed no pivot will enter on the right hand side. And in which case, I will be able to find, or at least claim, something about the inverse. So right now, this entry is a pivot entry. This entry can become a pivot entry provided I can use this to get rid of the entry below it. So let's do that. Minus row 2 added to row 3. So this is 0. This will be 0. And this will be basically 5/10 minus 14/10. So it will be minus 4 over 10, so minus 2 over 5. Okay. Is it? Maybe not. 14, oh, I'm sorry, it will be minus 9 over 5. Okay, so let me see. 1 half minus 7/5 is what we're trying to accomplish. 5 minus 14, so yeah, it's minus 9 over 10. So this will be minus 9 over 10. And if we have to perform the same things on the right hand side, 1, 0, 0, 0, 1/5, 0. And out here I have 1 half. This will be minus 1 half. And this would be minus 1/5. Okay. Now at this stage, if the question was asked to us, will this system have solutions for all the possible right-hand sides that I have listed here? The answer is yes, because if you look at this, I have rank of the coefficient matrix as 3. If the rank is 3, that means the rank of the augmented matrix in this particular scenario for any right-hand side will also be 3. Because the augmented matrix will have only 3 rows, so that it will have full rank. Therefore, it will be consistent for all right-hand sides. So, at least theoretically speaking, I can guarantee that this has an inverse. If only I can find the solutions to each one of them, then I will even know what my inverse would be. Okay. Actually, this example, or the way we have done it, should lead us to something which kind of pops out of it very nicely. what exactly are we after? Well, think of it this way. So far, what I have achieved is a row echelon form. You already have 3 pivots. What if I asked you, what would be the row reduced echelon form of this matrix? Remember, I'm asking the row reduced echelon form. It has 3 pivots. So in a row reduced echelon form, if it has 3 pivots, then it must be looking something like this. And since I'm talking about row reduced echelon form, all the entries in that particular column must be 0. Any pivot column will have only one non-zero entry, namely 1. So can I say that the row reduced echelon form of my matrix A must be this, as long as I have full set of pivots of full rank? So we have yet another criteria that we can at least think about, that the rank of A, if it is equal to n, assuming the size of A is n. Just let me remind it over here. I think I just put it somewhere over there. So if my matrix has a full rank, then it must be an invertible matrix, because then I will be able to solve for every right-hand side. Another criteria I can think from here is that the row reduced echelon form of A must be the identity matrix. Now, I'm not claiming that I have proven these statements. I'm just saying that these statements kind of become more or less obvious from the example we are doing. So that means these things could be true, and then we'll try to see if we can prove some of them. So what we are trying to do at this stage is develop criteria for a matrix to be invertible. One more thing comes out of here, which you can realize. The moment I said every row should have a pivot, that guarantees me no matter what I put on the right-hand side, for all right-hand sides, I will be able to solve the system. So if that is the case, then can I not say that if AX equal to B must be consistent for all right-hand sides B? But remember, we had talked about so-called row picture and the column picture. Every column that I put over here on the right-hand side, if the system is consistent, that means the columns of my coefficient matrix can linearly combine to produce this right-hand side. So can I say that the span of the columns of A must be equal to what? Let's see. You are saying no matter what right-hand side I put over here, I will be able to have a consistent system. That means every vector which lives in R3, for example, in this case, we will be able to express it as a linear combination of columns of A. So in that case, we can say the span of the columns of A must be the entire n-dimensional space. This is something which is very nice in linear algebra. If you do an example, and if you don't pay close attention to the numbers, you go for the sense behind it, then many of these results come out very, very nicely and very, very elegantly. In fact, it also suggests how to prove things based on what you have seen in an example. So again, let me remind you, I'm not saying that example is the proof of these things. It's just suggestive of how we are going to tackle this problem. All these criteria that I've written over here are equivalent. That means if the rank is full rank, then I can say the span of the columns must be Rn. So in mathematics, whenever we are trying to come up with a criteria, we try to see what are multiple ways which could be equivalent, so that maybe we can do this criteria and then everything else will follow. Maybe we can do this one, then everything else will follow. So it makes life a bit easy to deal with. Okay. What I haven't done in this example so far, I never calculated the exact inverse. So let's revisit that. So far, up until here, we guaranteed that it has an inverse. What it is will come from the solutions to this guy. And we know how to get solutions of a linear system. One way is I can just use this row echelon form and get the solution. The other way is I can go all the way up to row reduced echelon form and then read out the solutions. The nice thing about row reduced echelon form is, especially in this case, once you do that, you have the solution written out in front of you without doing any back substitution or without performing more calculations. So let's try to go for the row reduced echelon form. We already know what the row reduced echelon form has to look like. It will be just the identity matrix. Our only problem is just 2 extra computations. So this is fine. I will use this entry to knock the 2 above it. And then I'll worry about this entry a little later. Okay. So, I'll multiply the second row by -2 and add it to the first row and see what happens. So this will be 0 and this will be -14 over 5, so it will be giving me 1 over 5. This will remain 1. This will give me -2 over 5 and this will be 0. Okay. As you can see, I am seeing glimpses of the first and the second column kind of becoming what we expect in our identity matrix. All we need to do now is just fix this guy. So I'll multiply this third row by negative 10 over 9 so that I can achieve a pivot of 1. So here's the operation that I'm performing. I'm multiplying the third row by negative 10 over 9. So if it is negative 10 over 9, this will be negative 5 over 9. This will be 2 over 9. And this will be again will be 5 over 9. Okay. Now we will perform 2 more row operations to knock these entries out, the entries above 1. And once we have done that, we have achieved what we were hoping for. So from here we'll do the following row operations: -7 fifth times row 3 added to row 2, and the other row operation we are going to do is -1 fifth times row 3 added to row 1. So we perform those 2. Let's see what happens. The last row remains intact. Now, let's see what other entries will not change. Let's put them. Okay, minus 7/5 times row 3 added to row 2 gives you a 0 here. Minus 7/5 added to this will give you minus 7/9. And this would be 1/5 added to, what is minus 7/5? Okay, so it will be minus 14/45. So it will be minus 5/45 minus 1/9. And what else do we have? Oh, we have something over here. So minus 7/5 will give me minus 7/9. So this will be minus 7/9. Okay. Now we'll perform it on the first row also. Minus 1/5 added here will give you 0. That is exactly what we wanted to achieve. Minus 1/5 plus 1 will give you, wait a second, this is not right. This should be plus 7/9. Minus 7/5, okay. Now, okay, so let's perform it on the first row. Minus 1/5 added here, minus 1/5 will give you 1/9, 1/9 plus 1 will give you 10/9. Minus 1/5 times this. So here is minus 2/5, and I have minus 1/5. 2/45. Okay, and this will give me minus 18 minus 20/45, which is the same as minus 4/9. So this guy will be minus 4/9. And last but not the least, this will be minus 1/9. Okay. So this is the identity matrix that we have achieved. So we have been able to row reduce it all the way up to identity matrix. And whatever matrix I have got on the right hand side, assuming I did not make any calculation errors, this is the inverse of A. Why is this inverse of A? Because the first column over here is the solution to your first system. Second column over here is your solution to the second system, and so on and so forth. So in fact, this is the procedure we will be using to finding the inverse of A. You start with your matrix, you set up the same size identity matrix on the right hand side, do row reduction. If you are able to achieve the identity matrix on the left hand side, then the matrix is invertible, and whatever you get on the right hand side is your inverse. Usually, I could have gotten away just by telling this statement, but I wanted you to understand that how this criteria was developed. It was basically coming out of the existence of solutions to these equations, and that is how this criteria came into existence. So if I were to write down a test for this, I will say, I will start with this augmented matrix. I will row reduce it. And upon row reduction, if I am able to get the identity matrix on the left hand side, then the matrix is invertible. So if this can be done, then A is invertible and the inverse is we'll pick up from here in the next lecture.